I just want to
go ahead himself from this machine because the projection you are seeing is coming from this.
uh,
So you just unmute yourself from
Yeah.
your machine.
yeah, that's the thing I'm doing here. I just yeah, okay.
You just need to sign up this one. Then.
Is this one? No.
Something.
Okay, so yeah, I think it's not work.
Can you can somebody confirm from the in that they can hear it?
Hello.
Yeah, we can hear him now.
It's just every time there
Okay,
will
okay,
have some
okay.
message.
Okay, good.
Just I'm not sure. Let's try to remove the message.
we can yes, continue.
Oh, okay, okay, sure, yeah. Sorry for the interruption around here. So here actually it's just as a very go back and leave it. So here actually is just a very brief recap for the traditional SVMs method. So the thing here is we want to distinguish the glue point and the red point in the spaces. In the original space, actually, it's not quite easy to find some boundaries or the hyperplanes try to distinguish the two clustering. So that's the sense we want to project the data from the low space to the higher spaces. Higher space. In the higher space, we can easily to find some hyperplanes try to distinguish the red point versus the green point. The key point here actually is to do the projection. This is just a high level to make it more clear. The pictures in the left bottom shows is how we built the model. So this actually is when we use the projections, project the data from the low dimensions to the high dimension. In the high dimensions, our purpose is want to find straight lines, or maybe in the high dimensions, that will be just the hyperplane. So here for the illustration, it's just for the two dimensions, it's just the straight line. And our purpose is trying to maximize the margin. It's just showing here, so maximize the margin, and the the margins is just the 2 over R2 distance of the weight. Actually, it's equivalent to minimize the R2 norm of the weight. The second term here actually is allow or have some tolerance to outliers or to noise. This is will be add some slack variable. This is called the psi. In order they meet or subject to some conditions. This is the two conditions at here, and the C is just the hyperparameters control the difference between the R2 norm versus the tolerance for the outliers. So, any questions so far? No. In order to do that, the first thing is we need to compute the kernel of gram matrix. So, due to the kernel trick, actually, we don't need to implicitly transforming the data in that space in the higher space. We just need to compute the dot product between the 2 points in the higher dimension space. So this one is just to show the different kernel functions, and the mostly used one will be the linear kernel, maybe the RBF kernel. And let's talk about the difference between the SVM and OCSVMs, because our recent work actually is based on the OCSVM, so one class SVM. The biggest difference between each other actually here is OCSVMs, we need the two class data, but for our SVM need the two class data, but for OCSVM, we just need one. But if we need one, how do we build the hyperplane? The key idea is we view the origin as another cluster. So we want to find the hyperplanes that can distinguish between the origin versus this black point. So that's the high-level idea. And based on these intuitions, we can design our objective functions. As we can see that there has no big difference between the OCSVMs versus the traditional SVMs. The only difference actually here is, actually it's not a difference, it's just we involved a new hyperparameters, new here's, and this hyperparameters represents upper bound of the number of data layers. Actually, it's just as some outer layers around here. This is similar. It's just a controls how many numbers of the outer layers. And another one represents a lower bound on the number of the support vector. Support vectors is just as the point in the lines. We call it that is support vectors.
Okay.
Oh.
So you assume that the way in which this is set up is that the outliers are closer to the origin than the normal vectors. Most people would think the other way.
I mean, this is just if there has no hyperparameters mu, that a new definitely is not quite easy to find the lines to maximize the difference between the origins to the cluster. So that's the sense we involved the mu to control these outliers.
So if you would have a point which is right there in the
Yes.
outer corner,
Yeah, doesn't matter.
that would be counted as a normal.
Yes. So all the data points actually is in this kind of the cell, which is considered like this is normal. This one is element. Yeah. No matter this point is close to here or this point close to here, how far away from here. It's just if I need a point is far away from this hyperplane, which is considered like this is normal.
It really depends on application, right? I mean, not all applications have small, or close to origin outliers. We could have some very large outliers.
I mean, here actually is after the projection, after the kernel projection.
So
It's not the original species, it's up after the kernel projection. We project the data to the high dimension. Yeah, that's the same. If this is original space, yeah, you're right. There has some point is very close to the origin. But this here is actually after the projection.
So you are using
So
this.
if you have a powerful projection, basically the projection does all the work, right?
Yeah.
Then why don't you just project into positive and negative domain and be down with each other and having the master aligned there?
The thing is, how can you control the data projected to the positive and the negative?
I mean,
The thing is, you need, if you want to do that, you need the two cluster data. One is the normal and another version is abnormal. If
the normal is on the top.
I mean, what about the abnormal? If you want to use your integration.
What is everything else?
So because if you do that, there is no any abnormals around here. Yeah, it's just want to make it more clear. So let's see.
How you choose the projection? Do you manually pick the kernel?
The kernel actually there has a whole bunch of the kernels you can choose.
Well, of course.
Yeah,
you know that, but how do you pick one?
We just use the default one. We just use RBF. We don't specifically choose a kernel. We just use RBF to compute the kernel. And after the projections, you need to find the line. That's the point. How do you find the line? It's not how do you do the projection. The projection is just this one is just a several kernel function.
My point is use different kernel. When you use a linear kernel or polynomial kernel,
Yeah.
you get different results. Right?
That's true. That's true. Definitely that's true. If you use the linear kernel, definitely is when you project the data for this case, it won't work. So that's the thing we need to use a non-linear transformation, non-linear kernel instead of the linear kernels to project this data.
But then there's some terminology, although it's not labeled, but still there's some terminology.
Yes.
So it's like, I mean, compared to the other unsupervised learning, it sounds like there is more knowledge required.
Here I'd like to see is actually the kernel is fixed. Our purpose is not to choose what kind of the kernel. Is we just use RBF kernels, project the data to the high dimension, and after that, based on the projection, we want to find the line. How do you find the lines based on the projected data? That's the point. Yeah.
So okay, the assumption is after the RBF kernel is gonna be the output is gonna be first to that's something.
Yeah. Yeah. So does that answer your question? So this one is objective functions of the one class SVMs, and there's no big difference compared with the traditional one. So let's see the potential issue of the traditional. Sorry. Let's see for the traditional OCSVMs, what we do is suppose we have the n data point, x1 throws xn's in the RD's dimension. And the first thing is we compute the kernel. You can use whatever kernel you want, but the default ones is just to use a non-linear kernel or transformations. Here we choose is the RBF. And the training times complexity actually is n squared by d, because this is unbound matrix. And for each kernels, you need to compute the IoT distance. This is RD dimension, so that's essentially the time complexity is big O of n squared d. And when we after the training, when we do the testing, the first thing we need is the data point or the support vector, because we need to project the testing data in the kernel space. That's the thing we need the n data point, and the space is the n times d, because this is the d dimension. When we do the testing for the single data point, the time complexity actually is the same. So we project the data to the kernel space, and then we're trying to find the distance is far away from the hyperplanes in which set, you're either in the positive set or either in the negative set. Yeah, that's the high level. But the problems here is, as you can imagine, that if the n is very large, the computations of the grand matrix very expensive in time and space. So that's the biggest problem. So a natural way to address this issue is we want to find some approximated grand matrix using a lower rank of the grand matrix. The question is how can we do that? There is several ways we can do that, and according to the theorems of the kernel approximations, it states that suppose we have the kernel matrix n by n, and consider a subset of the endpoints from these endpoints. In the train set, there exists a matrix Q2 with rank D. This small d is very smaller than the capital D. Actually is a good approximators to the original kernel. So let's just lay in the middle. This one. So the original kernel matrix actually can be approximated with a K2. So in the detail is the first method is use a Nernstrom's approximation. First, since we randomly select the n data points from m data points from the n data points, and then we compute the grand matrix. This is the small grand matrix K m by n, and after that we compute the eigenvalue of this small one, and we just choose the top eigenvalue and also the corresponding eigenvector, and based on that we projected the data in this top k dimensions. We can reduce the kernel matrix. So that's the high level of this method. Any questions so far?
So this is your method, your proposal, this is somebody else.
I like to see this is someone else, but our method also is based on this one. This is just a part of the detections framework. There will have some other issues involved, and based on this, we address some issues.
You will talk about your.
Yeah, I will talk about that a little bit more.
To do the first step, when you randomly select m data point from the n data point set, to have the m much smaller than n, you have to make some assumptions such as the ground matrix have to be incoherence or something like that. Because if the kernel matrix itself does not have nice property, you can with type then randomly select a small subset will not give you enough the data point to pick from. So without those assumptions on the kernel matrix, I don't think it would the small m data point from the data, the data set.
That's a great point. So the thing here actually is m cannot be too small, but it's much smaller than n. So the error rate of the approximations error rate between the k tilde minus k distance is bounded by
Well,
m.
it can be very small. I mean, if with incoherence assumption, let's say it's mu incoherence, then you only would choose mu r log n.
Yeah.
Data point. Without the assumption, you will choose all of n. I mean, it cannot be, it cannot be too small. It's not, it really depends on the property of the matrix, right?
That's true.
So in the application, in your application, does the kernel matrix usually have good or bad property?
So
Inference property?
I mean, it definitely have the good properties. The reason is in the IoT environment, we assume there has, for the normal IoT devices, traffic generated by the normal IoT devices, the pattern actually is fixed, does not vary too much. That's the same for the kernel matrix actually have some good properties.
And how large m you usually choose in your application?
I will talk about that later. Yeah. So it's just I want to emphasize here is yes, you're right. The m cannot be too small. The thing is the approximations error rate actually depends on the m. So if the m is too small, the approximations actually does not work and actually does not need to be too larger. If it is too larger, there's no need to be this one. Yep.
You choose the m
Yes.
data points.
Yes.
And you compute the kernel out of those m
Yes.
instead of n.
Yeah.
Okay, and
Yeah.
then you do this. So Nystrom is pretty known.
Yeah.
Technique.
Yes.
So instead of selecting some rows or columns of n,
Yeah.
k kernel matrix, so you just select a subset of m and then do that,
Yes.
right? Okay.
Yeah. That's the point.
Thank you.
Any question? Sure, thank you for your question. So I will talk about the arms later. Actually, I'm here in the experiment we choose is m equals 100, but n is very larger than 100, or maybe 10,000, even more than that. So that's the same. The problems of the traditional one here actually is if we want to use the Nystrom's projections, we need to do the eigen decomposition. Also, there has the matrix inversion steps. This actually is not a good sense in the reality because some matrix does not have some inverse matrix. If you want to do that, you need to use the pseudo inverse. That's one way. Another thing is compute the eigenvectors, eigenvalue. This is time consuming. So in order to do that, actually we propose our method to use a random projection. This one actually is based on the Johnson-Lindenstrass lemma. This is actually just the basic idea is just to the random projections. The lemma states that for the original data point x in RD spaces, there has linear maps. We can project the data, any data points in the original spaces to the higher spaces or to the lower spaces. But the distance between any 2 points is preserved. So based on that, we can choose, we can approximate the kernel ground matrix with a random projection. And the steps actually here is the same, but the only difference is the second one. We don't need to choose, we don't need to find the eigenvector, eigenvalue, we just select the random directions projected through the random directions, the random directions. This is each item actually is from the normal Gaussian distribution. And after that, we can find our projection. And this lemmas shows that if we do that, even if this is just a random projections, the distance between the two data points actually is preserved. So that's the key point or the key intuitions of this method.
So
And
in the JL lemma, it is a random prediction. It can be seen as a random prediction, right? It has to be ellipses, and then the people found out that this can be a random prediction.
yeah,
Yeah. So my question here is like from this kn by n, why don't you directly just do a random prediction? So why don't you just sketch some rows and columns of the original K matrix?
so this actually is based on the randoms matrix D and by n. So if you randomly select the n columns about the key and band, there has no series guarantees this one works. So the reason we use the matrix, random matrix multiplied by the suburbs grand matrix key and band, because there has a work shows if we do this, this actually can meet the conditions in the higher space. So that's the reason we cannot just randomly select n rows from the original one. Yeah, because there has a paper, there has a work. The theory shows if you do this one, this can meet the good properties. Yeah, that's the reason. Yeah, thank you for your question. Any other questions?
Thank you for the intuition here, because I seem to be going further and further and further, and we seem to be only with the points you have selected, and you have properties to describe those points. But eventually, the kind of points you care about are your outliers.
Yes.
So it is really, I mean, again, I'm a bit computer scientist. For me, SVMs are nearest neighbors, right?
Yeah.
So what are you really doing here to the network, right? So all this kernelization and so forth, so from computer scientist point of view, you are messing with the distance functions, right?
Yes.
Right. So what does this thing does to the distance functions? I remember is messing up with distance function in a major way by introducing randomness in it and stuff like that. Will these classifiers really be?
I mean, the thing here is, if we don't do any projections, the grand matrix actually is in high dimension. If you want to do something in the high dimensions, usually it's time consuming. So that's the thing we want to.
Right, but as soon as you select this one randomly, then you just decide to use just the random scattering of your training data, right?
Yes.
And ignore the rest.
Yeah. But the thing is, this random projections can guarantee, even I projected the data to lower dimensions, the distance still be maintained or preserved.
So you want to come up with the faster method?
Yes.
To do that?
Yes.
So what is the, like, at the end, so what's a typical data set you deal with, and how computational intensive it is? Like how many points are, how much is it?
Yeah, I will talk about that later. Yeah, thank you for the question.
And then out of this, to reduce the complexity of the
Yes.
algorithm.
Yeah, definitely.
And so far, these are not you, these are lemma from somebody else.
The lemma is not us,
Yeah.
but here is our work. Our work is based on the kernel projections, kernel grand matrix projections, KGL. We call it KGL. This actually is our work. A part of our work. There also have some other things I will mention about later. Yeah. So thank you for your question. So the thing here is, if we don't do the random projections, the dimensions for the original projections are actually high. In order to save the time, in order to save the space, we need to project the data from the high spaces to low spaces. That's the thing we can save the time. Yep. Hope that I can answer your question.
So
extremely low situation, so
Yeah.
you have data in some dimensional space, right?
Yes,
You use kernel,
yes,
you move it to a higher dimension, and
Yes.
that's a known trick.
yes.
Then you are using another random projection. to
Come back.
bring it to, again, to the same.
No, it's not the same to the lower projection.
Again, from there to
Yeah.
another lower.
Yeah.
Okay, so, and you are saying that is good.
That's true. That's the same time. So the idea here is in the original spaces, in original space, the data cannot be distinguishable easily. So that's since we project the data from the low space to the higher spaces or the infinity spaces. In this infinity spaces, we can find the hyperplanes to distinguish the data point easily. But the thing is, in the infinity spaces, the time complexity is really high. So that's the thing we want to really project the data from the infinite spaces to even lower spaces. In the lower spaces, it still can separate the data, but the time complexity and the space complexity is really small.
In that projection, we reduce the sample size. From
Yeah, from the N to R.
from the higher dimensional space, when you project it to lower dimensional, you use the smaller sample size.
Yes,
Exactly.
yeah, that's another thing is, the first one is we don't use all the N data point, we just use a subset of the data point. Another thing is original space maybe is very large, and when we project it to the lower space, the dimension is very small, such as dimension equals to D. We project it to the 5 dimension, or original space maybe is 100 dimension or maybe more than that. Yeah.
So is it possible, like, so you're going the lower dimension, the higher dimension, then lower dimension?
Yes.
Can you go directly from the one to the?
It's-
Be more elegant, right?
Yeah, the thing is, if you from the lower space, original space to directly the final result, just use one projections, you cannot preserve the distance, or you cannot find the hyperplane that can be distinguishable.
You can make it. That's a problem. You should work on that.
Okay, I hope so I can adjust that directly. Yeah, next steps. If we can adjust that, definitely we don't need to this, all of this. Yeah.
Mathematics very elegant, right? So you don't look at-
You're right. Yeah, definitely. Yeah. There's some potential framework that I hope I can do something in there. Anyways, thank you so much for your suggestions.
I have to show that. It's
Yeah.
gonna be much easier because in the
Uh,
pocket, people get a lot, but if you use a few graphs like a diagram, it's going
Right.
to help you get in much better.
Okay. Thank you for your suggestion. So here is just to compare the kernel matrix versus our KKL's approximation. So the original ones, as we already mentioned previously, first instance, we need to compute the K and by N matrix, kernel matrix, and this is the training time complexity and the testing space and the testing time. And for our method, actually here is we use the projections, kernel projections, projected the data to a lower space, and the time complexities for the training, this is the time complexity. I won't talk about it too much on this. As our purpose actually is focuses on testings, not for the training. So for the testings, when we do this, actually we can reduce the time, we can reduce the space from the n multiplied by b to the n multiplied by b. This n usually is very small, is n equals to 100, n can be very large, 10,000, even more than that. And this small d is just a lower space you projected. And this one actually is even smaller, equals to 5 around in our experiment. Yeah. Any question?
Well, it's not question, just saying, for example, when it gets before those elements in there, obviously, and capital T is the largest one. I mean, it's not max of all those, but it is.
Yeah, definitely.
Result of the M and capital T, right?
Yeah. I just want to make existence more clear is for the steps we involved in the training. So definitely this one will be the maximum. It's just the
Yeah, same thing for the rest, you actually go to the max of the two,
Yeah. Yeah.
M capital T.
It's just in case if you have some questions around here, just to make it more clear. Yeah, this is a little bit messy on the. So for the testing, actually the same. We depend on the I multiplied by the D, because this is the original one, and this one actually is small. This one actually much more is majority based on the bigger lead. If this one is very large, this one don't make axis. Yeah. That's just our method. And any questions here? Sure.
Just quick thing, I'm back to I'm not in this area, I'm not following all these. But I'm just thinking from my statistics point of view, when you have these K, N by N matrix here, you're trying to approximate that
Yes.
using a lower dimensional.
Yes.
matrix.
Yes.
And you choose M data points at random.
Yes.
But N is much smaller than N.
That's correct.
But that smaller dimensional matrix, if I think in the form of a sampling, in repeated sampling,
Yes.
I will have, let's say, thousands of those ends.
Yes.
The approximate matrix. Yeah, thousands of them, maybe millions of them.
Yes.
Did you look at all of them in some way to see the behavior in repeated sampling?
No,
No?
that one actually is captured by this lemma. This lemma is just showing with high probabilities if we do the sampling, subsamplings in the with the high probabilities, this one occurs preserve the distance in the high dimension, in the lower dimensions versus in the original
Well,
space.
this lemma is from the value exists at the principal region. So
Yeah.
technically, this lemma only saying what you can potentially to you. Well, we'll pick a random app that potentially make you do this, and does not guarantee you will have this.
That's true. That's the sense with the high probabilities that we have something. It's just like you mentioned, we need to repeat multiple times just so we get a good result. Yeah. Yeah, thank you for your point.
So, I have a comment. So, the J or lemma is random projection, not random subset.
Yeah, this is just a random projection.
So, if you choose random subset, then definitely will affect the result. So, able to develop question because we have a design, okay, we of course, it's a different design, so we need to treat up on design point, this like design, you not to random design.
Yeah, that's a good point. Yeah, I think very good. It's a linear matrix.
Yeah.
That's why the structure, the distance structure is contained, right?
Yeah, it's
Yeah.
preserved.
So
Yeah.
this, I think it's really right, but if you just take a sample.
Yeah.
And it's going to be different.
Different.
So what's the best sample?
Exactly, so there's a design problem. So we don't have to talk about this. We can do it. The random design, the performance will be different. Every time the different subset, result is different.
Yeah.
So it's not optimal design, it's random. So it's definitely has some problem. So
Yeah.
I haven't heard of how you handle this issue.
And initially when you select M, they
Yes.
point out the big M. So you assume this is the kind of representative sample, unbiased sample, whatever, you assume that or simply an example from the sample thing, or do you have a particular rule?
So the thing is, we assume if we do the samples multiple times, we can get the good approximations to the result. If that's just the one specific sample, we need to do that several times.
So you are uniformly choosing the data points, so
Essentially say, suppose for example, if you
Yeah.
usually have one, let me use small number, say 1,000 data point.
Yes.
Suppose you want to select the 100 out of it.
Yeah.
So do you use simply the IID kind of sampling things or simple and sample things, or do you have a particular?
No, it's just the simple samples. Yeah, simple samples.
And you can make it actually to do for a small, if I need to large dimension, then you do. So if that's the case, that is actually almost like the random clinical trial, when you randomly assign the patient subjects to two treatments, and the same spirit.
That's true. It's just if you there is some theories show that. So if you do that one, you can get the good approximations. Yeah.
I know, I'm saying that to me, your randomly projection from your infinite kernel space into the lower
Yes.
small d thing, to me, this is exactly the same spirit as we random assign patients to different treatments. You do not guarantee good result, but you know it's insurance. You're just any system map bias.
I think the point here is, here we use the Gaussian's distribution.
It doesn't matter.
No,
I know, as long as this is, I'm okay with it. I think I got your point.
Sure. As we want to see is this is Gaussian's entries actually is projected to some specific directions. Yeah, that's the same.
In for more than one slide and it don't work.
So that's the traditional ones versus our methods. Definitely, we don't need to compute the eigenvectors, eigenvalue. And this is just the example shows if we use a curve KGL versus the Nordstrom's projections. The original one is just to show the data in the R2 space. And when we use kernel projections, also we use Nordstrom's projections, we can preserve the cluster structure, and also we can find the hyperplanes distinguish with each other easily. But the potential problem here is if we project the data to the lower space, use KGL or use Nordstrom's, the normal class is not necessarily the linear separable from the zero, but for the OCSVMs, the assumption is we require that it is separable from the original zero, origin from the origin zero. So in order to do that, we use the Gaussian mixed models, try to profile the projected data in the lower space. So that's the sense we address that. It's not just use the linear SVMs in the projected data. And here is just the sun is, I should have mentioned this because previously this is just the first thing is we project the data from the origin space to the higher spaces, or maybe this is infinity spaces in some scenario. And after that, we use the kernel approximations projections to the lower spaces D. And in this D spaces, lower spaces, we use the Gaussian mixed models, try to profile the distribution.
So in this case, I mean, can you just go directly because it makes it harder to take the numbering? Like you're using the SVM and all those things, because you can in principle can do that.
Yes. Yes.
Yes.
So this the thing is, as I mentioned, so let's see, for this data, if you use the Gaussian mixed model, so probably you won't get a good result. We did that. So if you just use the original data, run the GMM, Gaussian mixed models, you cannot get a very good result compared with.
What's the reason? Why
What I'm thinking is because this data actually is not separable in the original space. And if you use the Gaussian mixed models directly on this original data, probably it's not.
But I mean, you don't want to separate, right? The whole
Yeah.
idea of one class is you just have one class, you want to look at distribution. Anything that does not fall under the distribution is not, right? That's all the whole thing.
Yeah, the thing is, in the realities, the distribution is not just one distribution like here, or maybe have the different kinds of the normal devices generating different data. They will have the multiple clustering structures in here. If just use original Gaussian mixed models on the original data point, you couldn't get a very good result. So that's the thing we pretend to project the data to lower space. And another sense I like to see is if you use Gaussian mixed model directly, the time complexity is probably high in the original space. Let's see, original space is a bigger D. So you see here, this one is a bigger D. If we project this one is just a small D. So we run the Gaussian mixed model in a small dimension until it runs the Gaussian mixed model in the original space. This one is another factor. So,
but all those things we talk about in context of support recognition, right? So
yeah.
I'm saying that we don't need to use support recognition.
Yes, I understand. I mean, what I mean is, if I remove the other things, I just run Gaussian mixed models on here, this one will be affected because this one will evolve in our final result.
Because of having.
That's true. That's the thing I would like to see. If I project this to your dimension, I run the Gaussian mixed models, the time complexity is low with all of this one.
So what is your dimension with build up? What's the thing?
You mean this one?
Yeah, what
This one actually for the different data set we have a different dimension, the range from the 25 to around 125 around. So here this model is also fat. Yeah, this is just a fact.
So surrender, what's the dimension?
Yeah, that's just for our experiment. This looks is not too big, but in reality, if this is the image data, this is very high.
And your thing is more general, can be applied to images, not just in this.
That's true. Yeah, that's true. That's the sense. If I use a document model to come complexities and other issues I consider about is the topic design actually is trying to design efficient algorithms against the issue. Yeah. That's the thing. And here I don't want to mention too much. It's just a basic Gaussian mixed model. The problem is if you want to use Gaussian mixed models, how do you choose the number of components? This is a good point because the hyperparameters for the Gaussian mixed models definitely is based on that. And fortunately, Sir have some algorithms is called the quick shift plus. This can choose the case automatically. So the figures illustrate that if we use original model sequence algorithms, we can find the whole bunch of the clusters in each peak, but this one won't work. So that's the sense they propose some methods is trying to combine the different local clusters to a bigger one to have the less number of clusters and automatically to do this things. Based on that, we will reach out to our proposed projections algorithms. So the first thing is we use the kernel projections to infinity space, and after that, we use the kernel's grand matrix approximations to a lower space. And after that, we build models. Either we build based on the Nystrom approximations, or either use our KDL approximations. And after that, we use a Gaussian mixed model. So this is the higher framework, and it's our final framework. And I should mention this previously. I'm sorry for that. This is just our framework to do the things. Any questions in here?
So in this one, at the end, you still use the SVM or you can directly use the Gaussian.
You mean the PC?
So you are to detect the anomaly.
Yes.
You will use the one class stuff.
SVM, yes.
But did you just use directly the
SVM, GIM. That's the sense here we mentioned if we directly use the GIM, the original space is very high.
After you do that, right? So you have a very large.
Oh, you mean without the quick shift plus?
Yeah, I mean, so you have a larger space.
Yes.
You do the primary.
Yeah.
You have smaller space.
Yes.
You have the large space, smaller.
Yeah.
At the end, you have
Your space.
yeah.
Yeah.
And then can you put a Gaussian mixture?
Yeah. The thing here is if we want to use the Gaussian mixed models, how do you decide the D? Or how do you decide the key? So which means it's here. So if after the projections, if I want to use the Gaussian mixed models, I need to select the parameter. So that's the sense we use this method, the quick shift plus to select the key.
Okay.
After that, we use the Gaussian mixed model. Yeah.
Yeah, so at the end, you're using Gaussian.
Yeah, at the end, I use that. It's just that here is you need to find the parameters for the Gaussian mixed model.
Yeah.
Yeah.
So you could give it this thought without getting into one class separately. It's basically Gaussian mixing.
Yeah. Yeah.
That will probably really simple. People don't need to know all the things.
Yeah.
At the end, the Gaussian mixing is very intuitive, very simple. Right?
I like to see is because we want to design some efficient algorithm, so that's the thing we need the kernel. Another thing is when we project the data to the high species, this makes the problems more easier. Yeah, that's the thing. So this is just a framework we also mentioned about, and here it just is algorithm. The first thing when we do the training, project the data to the birth space, approximately the kernel use Nystrom or KDL. And after that, we built the Gaussian mixed model, and then we trying to project. We return build the Gaussian mixed model life, and along with the projection side, and also after that, when we do the testing, it's just a projected to lower space, and then trying to recognize what is the difference between the projected through some processing threshold T, and if it's less than the threshold, this is also a layer. Yeah, that's the framework. the rest of them actually is just the experiment evaluations. We computed the data to several data sets. There has malicious traffic, also there has a normal traffic. There has some public data sets, also have some synthetic data sets. I won't talk about too much on this, it's just for the time. And here it just shows the different data we use. And this is just the data size and the dimension. And the range we talk about, the dimension is from the 15, oh, sorry, previous dimension is 25. This is from the 15s to 121s around. And our evaluations matrix here is we use AUC, testing time, and also for the space. So this is high purpose. So first thing we focus on the accuracy, and also we focus on the testing, the efficiency, and the space required. And this is the devices. When we deploy the models on the variety of the devices, one is the server, another two actually is just the IoT device. This has some resources constraint. And then this is just the experiment result in the main paper is just show the best result with the best parameter. We also have the default parameters. We did that all the sense. We show that all the result in the appendix due to the space. So the projection dimensions actually d equals to 5. The number of the subsamples, small m actually is equals to 100. And I hope that can answer your questions previously. Here is just the baseline algorithms. If we use the PCA, it's not PCA, if we use OCSVM, what is the performance of this one? And the first one is the AUC. The second one is server train time, and this is testing time, and this is the space. How much space do we need? And we repeated each experiment 5 times, and we then computed the mean and standard deviation. And this one is just to show the best performance. For the train time, so here is our algorithm's performance compared with OCSVM. As we can see, there's no big improvement, but that's okay. That's not our focus is on the training. Our focus is on the testing. So as we can see here, this is our testings. If we use the KGL's projection at the top for the testing speed, speed up, this is from the 20 times, or maybe for some data sets will be the 40 times speed up. This is a speed up, and this is for the testing time speed up. Because our method actually does not related involved on the original, and we just involved in the small m. So that's the same. Another one is, let's see if I use a Nordstrom's algorithms, what is the performance? Yeah, that one is just to show the performance of this one. From the result, we can see that even with just a random select a small subset of the data point, we still can get a very good performance. And the next one actually is just the summaries of this work. This is we can get the 10 to 20 times speed up in general, even for some data set we can have the even 40 times speed up. And also for the space, we can have the more than 20 times speed up, space reduction. And here is the advantage of our method. We don't need to label the data, and this one can be deployed on the resource constrained device. And another thing is, if we want to deploy the models in the new environment, it's quite easy to implement. Another thing will be just some limitation. So we assume currently we have the access to the other data, but it does not always hold in practice. Let's see if the data distributed across the devices or across locations, what we can do. So there we have some others approach based on the federated learning. So they can build the models, or learning the models, even the data across the different devices or the different location. That will be another topics because of time, so I won't touch that too much. And another one I'd like to briefly introduce my research interest. It's just the first one is deploy the efficient, safe, robust machine learning algorithm, and another one is try to use this ones to address the real world issues, maybe in the cybersecurity, or maybe in the NLP, or maybe in the finance. And this one is some previously, it's just a quick previous work. Either one is on the machine learning. Machine learning's model efficiencies, we already mentioned about that. Another one will be the robustness and safety. Another one's for the application for the cybersecurity. Here we mentioned about anomaly detection. They'll also have the network traffic identification, and also for the finance will be the salary clustering, and also for the regression. That's pretty much all that. And thank you so much. I'm happy to take any other questions. Sure.
How do you play computer memory with space? I have never done that. I mean, every time I talk about memory complexity, I always manually calculate the zero for.
Yeah.
Seems like you go on to the very detailed 100 kb setting.
Yeah.
So what software do you use over there?
Oh, it's not software. Is when I store everything on the, let's see, so once I build the models, I can extract the parameter, and once I extract the parameters, I just dump them to the disk, and the disk will show you how many KB you will have. So that's the sense we can compute the C. Yeah, this is manual. I'd like to see it's not just a manually. I'd like to point out. Bear with me.
But you don't know if maybe the other part of your computer or Windows is using something, right?
That's true. So let's just see here. This actually is our
I mean, I know how to calculate it.
Yeah.
But my question is, because later when you have a table to this,
Yeah.
how many things you use, I'm just curious how you do that. I mean,
Yeah, I understand your question. I mean, for the surrounding waves, actually, we have this one, and for the experiment, what I did is just manually. Once we have the parameters, I dump them to my disk and see how many KBs, and they also have the Python libraries. You can call the Python libraries to get the how many space required from the parameters extracted from the algorithms you have. So that's the ways I did that to achieve the.
But see here, if I'm working on synthetic problem, I mean, if you use software, I guess it may be more accurate. If I do it manually, I mean, sometimes I have to create a problem. The problem itself, not necessarily, the memory size I have to use it for the algorithm itself.
Yes.
So I later have to verify whether I have a blown truth solution or not. So and validate my result, right? So I'm just saying manually doing it seems not very accurate to me. But I mean, of course, if there's software, a Python library, I believe
Yes.
it's probably working in a more process way.
That's true. Yeah.
Okay, but that is a quick question.
Sure.
Another question, can I go back to maybe, I think the 24 or 25, 24, 22, like that? When you have,
This one?
this one, exactly this one.
Yeah.
Can you use?
Shoot.
Okay, so, we remember earlier we talked about, the one class vector support machine, SVM,
Yes.
or vector machine, that based on the outliers are close to the origin. But then with these two different projections, you see like, it's shifting, right?
Yes.
I mean, in the middle one, the red component is more close to origin, while on the right hand side, the green class is more close to origin. So
No, it's not.
it's not.
No. Both of the zeros are this is the zero on this one.
Oh, I missed the right. I see.
That's the zero on that one.
Okay, so if I consider outliers in this picture, the red component will be the outliers.
The thing I should mention here is, this one actually. So let's see here. So if this is our real data, all of them, no matter the red one or the red ones, we consider that it's just a normal data. We could
But
just,
that's if it be class, if it be one class, right?
yeah, one class. It's just
If it
all of them.
class, with your assumption, the red component will be the outliers.
Actually, you see the orange, this one is outlier. If you want to find some the hyperplans, you will consider all this one here. You see here. So this is origin. this one will be zero. Normal, this one is just overlay.
So if somebody, so if somebody wants to be.
Yeah.
Obviously, this is an example which is like the toy example, which is teaching. Like I'm teaching an undergraduate class, and this one is a toy example.
Yes.
Which you are showing. And in this particular case, the outlier identification is really easy.
Yes.
Right? Because it's like your points, the outlier points are farther from the origin in the original space.
Yes.
So I'm just pointing out that this is a very bad example. Okay, this is very easy to identify outliers. The red ones are outliers, the green ones are yours.
No, but he's saying the outside, he's saying the green one is outside.
No.
All these, I'm sorry,
All of this actually should be considered about the normal. If there has no outliers, all of them should be considered about.
Of course, with the speaker, we know this to normal class, but I'm saying with the way you do
This
the
one
people
here,
over there, right? I think like more close to outline. Yeah, the way I understand is that more close it near to the organ.
what is the outlier?
more- It's more outline. right?
Yes,
So okay, I guess my question is, if it's eastern slice more close to origin, or it's more like toward the circle
yes,
of the coordinate system? Which way it is, because see, to me, it seems like the red component is more close to origin, but the green one is more toward the
Yes.
color.
yes, I saw your point. So you said this one will be the outliers because this one is very close to the origin.
Right.
The problem here is this one is actually, if you want to use the OCSVM, you want to find something that is very far from the origin, but this one is very close. Even this one, that should be something, this one should be more clear. So if you want to find the audience, all the things around here in this one.
Right.
So that's the thing is, this picture I just want to show after the projections, the normal class is not necessarily linear separable from the origin. From the origin, it's just want to show you that there will be have some possibility. This one just one case, but the other case will be something like this. Yeah, as a professor mentioned, maybe I need to find some better examples that makes sense, try to make it more clear. Yeah. Does that answer your question?
May I ask a question?
in this your three plot on top one, when you created this plot, did you use the information about three different colors, or actually you don't?
I don't
You
actually.
don't.
Yeah, I don't.
Essentially, this color essentially just indicated what your point. Actually,
Yeah.
when you did all the simulation, all the character thing, you do not use the color information, right?
Definitely, because this is unsupervised.
So in this case, then it's more about the presentation, not about the identified outline.
That's
So
true.
you can
This,
just label any color one to.
Yeah.
See it.
yes, in the reality, this is just a one color. It's just one color. For here, it's just an illustration.
So this one essentially you want to show us that you
Yeah,
you do different kind of a projection, you can see what kind of a pattern would be.
Yeah.
Right.
yeah, that's just for the illustration. Makes sense and more clear. Yeah.
Okay, well, I have a question. So you seem to be living in an SVM world.
Yeah.
You didn't show any comparison with any other technique.
What do you mean? Any other
I
technique?
don't know, I'm teaching a machine learning class and it's maybe one lecture after the right?
Okay, I see your point. So here, our purpose is to want to see our method is better than traditional OCSVM. Definitely there has others.
OCSVM is not a very dynamic technique.
I know there has some other.
It's under no definition
Yeah.
is the state of the art. It's one paper which had been published maybe 25 years ago or something like that. Right?
Yeah.
It's not state of the art.
I mean, there has some other method, let's see, it's based on the deep neural network, autoencoder, etc. method. So for here, our
any cluster.
yeah, I understand. I would like to see this work actually, like you said, there has some limitation. We just compare with traditional OCSVM. We didn't compare with some others. One class machine learning method, such as deep neural network, or maybe some other methods. Yeah, that's true. It's just some limitations of current work.
Follow that in the line or something. So I'm not familiar with your technique or whatever, but I just think that to me, the value of your what you're doing is that, to me, essentially say three things. One is when you have big large data set, you do something from a small subset of that.
Yes.
And then you create it from lower, although it's a low number of observation, but you use kernel, make it infinite dimension thing. When you do the random projection until reduced to lower dimension as well, then you use like GM, whatever method. I don't mind if you whatever method you do or Gaussian data. But I'm wondering, so it's actually should value that. I'm wondering that is there any other places, other methodologies people have used this kind of sort to work on? So for example, you using on the one of the techniques, Professor just mentioned that it's maybe the only result of 25 years ago. I'm wondering if you do not use that one with other techniques or other methodologies, actually this line of thoughts will still valid, or you have seen some people do that.
So I like to see is, yes, this is just a one method based on the OCSVM. There also have some other method previous work. I like to mention that is not this one. Let's see here. Let's see, this is our impervious detection framework. Actually, it's based on the deep neural network. It still is one class related framework. But here it's just use autoencoders try to build the model. So this is another method you can adjust the ratios, compare with OCSVM. Yeah,
Good thing.
yeah, it's just another method, and we just built the profile the normal users behavior user autoencoder. It's based on the deep neural network, and after that we do the rest of the things. Yeah, that's some. Yeah, it's a similar idea. Hope that answers your question. Any other question?
May I ask a question?
Okay. Thank you so much for your time.
Hello?